We're going to take a look at number 7 in Achieve section 4.4. We're going to determine the intervals on which this particular function is concave up or concave down, and we're going to find the points of inflection. Now there's lots of instructions. I copied some of them down, so you want to pay close attention in these sections 4.4, 4.3, where you're given a lot of information and they want it in a certain format. So when it comes to the points of inflection, you're going to give your answers a comma-separated list of points in the form, X comma Y. Basically, the asterisks are the numbers you fill in. And you have separate, if you have more than one point, you separate it by a comma. Enter DNE if there are no points of inflection. So that's real important to understand that for points of inflection. Typically on a test or something that I give you, I typically just want to know the location of the points of inflection. So I would just say, give me the values of X where we have points of inflection. Of course, to get the Y value, simply plugging into the function those values of X. And then intervals of where we're concave up, concave down, you're going to use interval notation. So this almost looks like the same thing, but notice this is an interval down here, not a point. And so it is important to choose the correct type of parentheses. Typically for intervals of concave up, concave down, though, you're always using the parentheses, not the brackets. Use the symbol infinity or minus infinity, the union symbol for combining intervals. And then if are no intervals where a function's concave up or concave down, you use this symbol right here, which is down in that palette, math palette, when you're entering expressions, the empty set symbol. Okay, so in this particular problem, I would, of course, to find out about concavity and points of inflection, we need the second derivative. So we need to take the second derivative. Which means we need to take the first derivative. But some of you might say, well, I've got a product here, right? X minus 6 times the quantity 1 minus X cubed, so I want to use product rule. You could do that, but it's so much easier to go ahead and FOIL this thing out, because we could do that and not use the product rule, right? So let's FOIL that thing out, rewrite it. First, X times 1 is X. Outer, X times X cubed, or negative X cubed, is negative X to the fourth. The inner is negative 6 times positive 1. And the last is negative 6 times negative X cubed, or positive 6X cubed. And now just take the derivative of that. No product rule required. Derivative of X is 1. Derivative of X to the fourth. Derivative of 6 is 0. And then the derivative here, bring the 3 down. I get 3 times 6, 18 X squared by the power rule. Okay. And then I need the second derivative, right? The derivative of 1 is 0. Here, bring the 3 down. Notice that's a negative 4. So it's going to be negative 12, X, subtract 1 from 3, 2, negative 12X squared. And then the derivative here, bring the 2 down, 36X to the first power. So here's my second derivative. Pretty easy to do. If you use the product rule, you still have to simplify after you get the product rule to get down to this, but you should get the same result. Now I'm going to go ahead and factor out from here the GCF of negative 12X, right? So between negative 12 and 36, I factor out a negative 12, and I've got an X and an X squared, so I plot an X. That's going to leave me an X and a negative 3. Notice the negative times negative will make that positive. So I can see clearly that the second derivative is 0 when X is 0 or 3. And now I just need to confirm, don't assume that these are locations of points of inflection. We need to make sure there's a change in concavity. So we always want to do a sign check of the second derivative in this case. I do it this way, right? With the number line here, the values of X are 0 and 3. The second derivative is 0 there, as we just said. And then I just need to check some value less than 0, some value of X less than 0, and find out whether the second derivative is positive or negative. And then the same for some number between 0 and 3 and some number greater than 3. If you plug in like negative 1, here I have negative 12 times negative 1 is positive 12. Negative 1 minus 3 is negative 4. Positive times negative is a negative. If I plug in something between 0 and 3, like X equal 1, I'll get negative 12 times negative 2. Negative 12 times negative 2 is positive 24, positive. And then something bigger than 3, like 4, if you plug it in, you'll get a negative times a positive, which is negative. So this is a sign check. And then from that, we can answer the questions. We do have points of inflection at X equals 0 and X equal 3 because we have change in sign. We're changing, right? Basically, when we're negative, we're concave down. When the second derivative is negative, which means the first derivative is decreasing, That's the definition of concave downward, is when your first derivative is decreasing. Second derivative being positive means our first derivative is increasing, and that's the definition of concave up, when your first derivative is increasing. So we do have points of inflection at x equals 0 and x equals 3. What they want you to get is the y coordinates, because they want points actually listed, x, y points for the points of inflection. So I just go back to the original function and plug in 0. If I plug 0 into the original function, I guess it's right up here. I'll just get -6 times +1, which is -6. If I plug in 3, I'll get -3. 1 minus 3 cubed, 1 minus 27 is -26 down here, and then multiply them, I get +78. So when you list the points of inflection, you're going to do 0, -6 and 3, 78. On tests, I'll typically just say, give me x equals 0 and x equals 3. F is concave up. We've already said that, where the second derivative is positive. So on the interval from 0 to 3, notice I'm using parentheses, right? Not including. So it's concave up on that interval between 0 and 3. And then concave down for what? Values less than 0. That's where I use the negative infinity symbol to 0. And then the union symbol, 3 to infinity. I forgot my parentheses there. Right, for this other interval. Okay. So there's all the analysis for this problem. Hopefully this makes sense for you.